Hi everyone, this is Baxi Chong. In this video, I will briefly introduce our work to move sidewinding forward, optimizing contact patterns for limbless robot via geometry mechanics. Before it starts, let's take a look at the general snake locomotion. Lateral undulation gaits are commonly seen in many biological and robotics limbless robots. However, lateral undulation gaits cannot produce effective gait motion on hard ground, as you can see from the example video here. In this way, what can limbless robots do on hard ground? Sidewinding is one of the most effective snake locomotion gait on hard ground. During sidewinding, the body modules are periodically make and break contact with the environment to generate thrust in the desired direction. So, how should we understand the sidewinding? We propose to use geometry mechanics to study the sidewinding problem. In geometry mechanics framework, the configuration space is decomposed into the shape space and the position space. The environmental ground reaction forces are encoded in the local connection matrix, where the velocities in the shape spaces can be mapped into the velocities in the position spaces. Thus, the net displacement can be approximated by a line integral in the shape space, as you can see from the example here. According to the Stokes theorem, the line integral equals to the area integral of the curl of the vector field. Thus, we can visualize the kinematics by the curl of the connection vector field, which is called height function. Here, we show the vector field and height function of limbless robot moving on hard ground. The vector field is almost curl-free, leading to low amplitude in the height function. So, what about sidewinding? In sidewinding, there are many contact states. For each contact state, the vector field is almost curl-free. As you can see here, we showed 3 contact states and its corresponding almost curl-free vector field. Apparently, its height function has low magnitude. But what if we can partition the shape space according to different contact states? In this example, we showed that if we can properly partition the shape space by 3 curl-free vector field, we can create a new vector field that has large curl, which provide the basis for the sidewinding. But how should we partition the vector field? From the Hodge-Thompson decomposition, any vector field can be decomposed into the sum of the curl-free component and the divergence-free component. During snake locomotion, the curl-free component is in general have greater magnitude than the divergence-free vector field, especially in our case on hard ground. The line integral in a curl vector field is equivalent to the height differences in the end of the endpoint in their potential functions, and it's path independent. For these contact states, we can derive 3 potential functions. Contact pattern partitioning in vector field can then be converted to choosing the appropriate transitional points. We can then choose the optimal endpoint from the potential function differences. We apply our work to generalize sidewinding for reduced number of joints. The conventional sidewinding formula works fine when we have sufficient number of modules. But in the case where we don't have enough modules, the sidewinding formula can then produce unstable behavior and rotation emerged. Using our method, we then generalize the application of sidewinding to robot with reduced number of joints. As shown in the result on top right corner, the locomotion performance of the 6-link robot can be as good as those with 12 links. Unlike those on granular media, modulating the amplitude cannot change the direction of the motion on hard ground, but there are applications where we want the robot to navigate with a different direction. Our method can modulate the direction of motion by choosing different contact patterns. In conclusion, in our work, we extend geometry mechanics to optimize, analyze, and design the contact patterns. And we apply our work to modulate the angle of motion for sidewinding robots moving in isotropic environments. We also use our method to design the sidewinding gate for 6-link robots. For more detailed derivation, please find our paper from RSS.